Good morning, everyone. We have already finished the chapter 40. I hope you feel good so far. Yeah, like I said, it's there are too many things you need to review, but the most important thing I have already talked in our classes and for the simple harmonic motion. And what you focus is on the simple harmonics can be represented. Simple harmonic motion can be represented by a sinusoidal function. So yeah, you can represent the displacement, represent the velocity, represent the acceleration, using a sinusoidal function, and also you can see all the simple harmonic motion, yeah, because the net force is always linear with some variable. For example, the spring is linear with a displacement, and the pendulum is linear with the arc length. Yeah. Uh, that is the most important thing we need to know. And also, what we need to know, about the simple harmonic motion is the simple harmonic motion. You can see the kinetic energy and the potential energy. It can be transferred with each other. Yeah, and the total is constant, and it will transfer with each other. And like we said, the connect energy and the potential energy, it will be always constant. And also for the simple harmonic motion, and we can consider the most simple harmonic motion as a spring motion, or a pendulum motion. And for a spring or for a pendulum, we can use some equations to decide the uh, frequency and period we have already talked about in our class. And those things are the most important thing in we have already learned. And we talk a lot, and many there's applications how we use this theory to resolve some real problem. For example, because the simple harmonic thing, harmonic motion, and we have a resonance, a phenomenon. Yeah, and also you can see in the real world, the simple harmonic motion is not continuously. It is damping, damping, oscillation, because you can see in the real world there is a friction. Yeah, so. This is what we have learned in the oscillations. And okay, before I talk about today's class, traveling waves, I want to clarify something. Let me share my screen, and you will know that. Uh, okay, yeah, and let me have this. And as you can see, this is synthesis 40.1 describing simple harmonic motion. Actually, this is very important, we talked. And this is position, velocity, and acceleration of objects undergoing simple harmonic motion and sinusoidal functions. Yeah, and some students ask me, why why the maximum displays equal A. I think this one is obvious, because you can see the cosine is the range is from -1 to 1, so the maximum must be A. Yeah, but why the maximum velocity is equal this one, and y is maximum acceleration equal this one. Does anyone knows? this why it is this thing. Yeah, actually, I want to like explain that. You can see. Let me try to write it down. Uh, yeah, and I will like uh, try to write. I will write it here temporarily. And you can see xt equal what a cosine 2 pi f t. Am I right? So what is velocity? Like I think you have already learned this. Like the v equal what? V equal s divided t. Like in the specific time, what's your like displacement? Am I right? So here the velocity is just in a unit time. What is the distance? This is the equation for the velocity. The velocity also can be represented in the unit time. What is the how much how many displays this object take? So which means the vt should equal dt dxt dt. Like we will differentiate this equation. Yeah. I think differentiate this equation, you have already learned that, am I right? Like d, which means d a cosine 2 pi ft dt. And this is exactly 2 pi f, like a cosine 2 pi f, cosine will become sin, sorry. Yeah, because differential and cosine will become sin. So you can see, yeah, it's just like a you can see the Vt here. It's just equal 2 pi. Sorry, I need to put it here. 2 pi f sin 2 pi ft. Yeah. So which means here there is like a maximum velocity. I'm right. So yeah, maximum velocity is just this part. Does it make sense to you? Yeah. So that's the reason why the maximum velocity equal 2 pi fa. Does it make sense to you? Yeah, and the similar thing, the acceleration is just the equal like the at just equal dxt dt. Yeah, so the not dxt dvt vt dt. So which means it the velocity will equal like this equation, like do a differentiation, and you just replace maximum velocity with this one, and then you can get the maximum acceleration. Yeah, does it make sense to you? Yeah, this is why this is how get the maximum velocity and maximum acceleration. Yeah, this is what I want to share more for today. And so like yeah, it's a little mess up here. Let me try to move it. Okay. Let me try to remove all these things. I think that's fine. It will not affect you to see these words. I'm right. Okay, let's talk about the today's thing, traveling waves. Actually, yeah, this is a very like a common phenomenon in the real world, and you will know why it's just like that. Yeah, you can see like for the chapter 15, we will learn traveling waves and sound go. And to learn the basic property of traveling waves, and you can you think what is traveling waves? And firstly, let's to see what is waves. Yeah, waves like a yeah, you can see if you drop some like a thing into a pond or into a lake, and there will be some like a water wave. Yeah, and if you like weave a string, and this string will generate a waveform. Yeah, and for the water for the stream, and you can see this wave. But there are lots of waves in the real world. You cannot see it. For example, the sound waves, the light waves, and and other different waves like electrical waves, magnetism waves. Yeah, many waves. Yeah. But those waves have some specific rules, and we will learn those waves and in this chapter. Um, okay, and let's preview this chapter 15 and to you guys will know we will learn in this chapter. And for the traveling waves, and I think from the name you can obvious to imagine that, like shaking one end of the spring up and down causes a disturbance. It will generate a wave, like this wave to travel along the spring. Uh, oh, sorry, let me try to, yeah, like if you shaking from here and to generate a wave. Yeah, you can generate a continuous wave. Yeah, that doesn't that's fine. And this wave will travel along this spring. This is a wave, and usually the wave has the property like traveling. It will travel from one end to the other end, from one position to the other position. Yeah, you will learn the wave model that describes a phenomenal region from light waves to earthquake waves. Yeah, you can see there are actually in the real world there are so many waves. Yeah, we will learn that, and you will see most waves can be like modeled in a specific form like that. Okay, and also we will learn how to describe waves. A wave moves out from the vibrating rod. The signal wave you can see here. If you put something into here, and this is a water wave, and this water wave you can see it's very familiar. It's up, down, up, down, up, down, up, down. Am I right? Yeah, it's a sinusoidal form. Like we have already seen this sinusoidal form in the chapter 40 oscillations. Yeah, actually the wave and the oscillations have some relationship. Yeah, we will talk about later. And the terms and the equations used to describe waves are closely related to those for oscillations. And yeah, we will talk about that. Okay. And we will so far we will learn what is wave, what is traveling wave, and how to describe waves. Yeah. And then we will learn like the energy and intensity. Yeah, all waves carry energy. Yeah, the energy of a laser beam can be used to burn away unwanted part of the cornea in eye surgery. I think I don't know if you you guys do this similar surgery, and this like light, this laser, yeah, this like a laser beam, it will have a light wave, and this light wave can burn away unwanted parts. Yeah, so you will learn to in this chapter you will learn how to represent the energy, how to calculate the energy, how to calculate the intensity, a measure of how spread out or concentrated a wave's energy is. And you can see the wave will spread. Yeah, so how can this wave spread? How to calculate the intensity? Yeah, this is for the chapter 50, and we will learn those things. Okay. Also, let's looking back the simple harmonic motion. In chapter 40, you learn to use the terminology of simple harmonic motion to describe oscillation. Am I right? Most simple harmonic motion can be described as most simple harmonic motion to describe oscillation can be represented as a sinusoidal function. Does it make sense to you? The term you learned such period, frequency, amplitude. This is amplitude. Yeah, amplitude. Yeah. and will apply to description of wave motion as well. Yeah, you can see for it's just similar like a wave, am I right? So what we have already learned in chapter 40 also can be used in chapter 50. Happy, am I right? Okay, we don't need to like get used so many new things. Okay, and before we talk about the traveling waves, there is a question. Let us stop to think. There is a wooden toy hangs from a spring. When you pull it down and release it, it reaches the highest point. Sorry, let me charge my laptop. Okay. It reaches the highest point of its motion after 1.0 seconds. What is frequency of the oscillation? Actually, I think this one is familiar to you. Am I right? We have already done so many like questions in chapter 40. Like here, like we put this mouse, we put this mouse down and release it. It reaches the highest point. This is the lowest point. We point it to the lowest point and reach to the highest point. And after 1 second, which means from the lowest to the highest, you need 1 second. So how long will be the period? So what's the period? You can see this is half period, am I right? Like I said, if you from the lowest point to highest point, from the highest to lowest point, this is a one period. Yeah. So half period is 1 second. And so uh, the period is what? Yeah, it's 2 seconds. Am I right? And what is the frequency? Frequency equal what? Frequency equal 1 over t, am I right? Now t is 2 seconds. So it is 1 over 2. What is the answer? 0.5, am I right? Yeah, so it's easy. Am I right? So these things will also be used in chapter 50. And okay, this is today's goal. And firstly, we will learn what is the wave, what is a traveling wave, what a wave, and learn the wave model. And then we try to understand the traveling wave. And finally, we learn how to describe waves graphically and mathematically. Yeah, this is today's goal. And if you have any question, just let me know. Okay. Let's see like the section like 41, the wave model. The wave model like describes the basic property of waves and emphasizes those aspects of wave behavior common to all waves. Although sound waves, water waves, and radio waves are clearly different, the wave model will allow us to understand many of the important features they share. You can see there are many like example waves. Sorry. There are many example waves. The water waves, I think we like usually see it. The land waves, yeah, sometimes you can see it, but mostly you cannot. And the sound waves, yeah, you can hear the sound, but you don't you cannot see the sound. You cannot like yeah, it's not invisible. It's not visible. And for the microwave, yeah, but the micro when you heat the like food, actually inside the microwave there are some like waves, and we also cannot see it, and also radio waves, X-ray waves, and ultraviolet waves, and some seismic waves. If you can see when the earthquake happen, yeah, there will be some seismic waves. There are so many waves. It seems different, am I right? It seems different for us, but they will share some like same features. Yeah, we call it wave model. Yeah, we can model those waves. Yeah, and let's see a term called like mechanical waves. Mechanical waves are waves that involve the motion of the substance through which they move. The substance, we call it the medium. Yeah, like the mechanical waves are the waves that involve the motion of substance through which they move. Yeah, like for example, if you drop something in the water, sorry, if you drop something in the water, and what this is a mechanical wave, am I right? So what is a medium? is water, am I right? So because this wave moves in water, a disturbance is a wave that passes through the medium, displacing the atoms that make up the medium from their equilibrium position. You can see the disturbance is a rippling of the water surface. This is a disturbance, and this is the water is a medium. Am I right? So this is some like terms we need to know. Okay, for the mechanical waves. And a wave, this disturbance is created by a source. Yeah, usually there will be a sorry, there will be a source. There will be a source to like generate this disturbance. Once created, the disturbance travels outward through the medium at the wave speed v, and a wave does transfer energy, but the medium as a whole does not travel. Yeah, like the water, it will not travel, but like the wave will like transfer the energy. A wave transfers energy, but it does not transfer any material or substance outward from the source. So like the water is there, the water will not be transferred to yeah to somewhere. Yeah, the water always aware, but there is some energy. You can see we drop a stone. There are some like energy. Yeah, if we drop a stone, there will be some kinetic energy, and this energy will like will be transferred uh will be transferred by this wave. But we cannot change the any material. We cannot make the water to one like Jesus, am I right? Yeah, so like this is mechanical wave. This waves just generated from the energy. Yeah, does it make sense to you? Okay, let's check the other two like important terms. We call it transverse and longitudinal waves. Okay, actually most waves fall into two general classes, transverse and longitudinal. And what is transverse wave and what is longitudinal wave? I think many students may have heard about it, and let's explore it more. Actually, for mechanical waves, a transverse wave is a wave in which the particles in the medium move perpendicular to the direction in which the wave travels. You can see here, this one is a this one is a transverse wave, and you can see the wave travels direction. It's just like this, and the particle in the medium, they just moves like a perpendicular, like they move up down up down up down, and this is a wave, like a wave direction, and like the particle in the medium move perpendicular and to the direction in which the wave travels. This kind of like a wave, we call it a transverse wave. Shaking the end of a stretch string up and down creates a wave that travels along the string in a horizontal direction, while the particles that make up the string oscillate vertical. Yeah, actually, like this, the particles in this string that makes the make a string oscillate vertical. Yeah, but the wave travels to this direction. Yeah, this kind of like wave, we call it a transverse wave. And the other one, we call it longitudinal wave. Like the particle in the medium move parallel to the direction in which the wave travels. You can see here, this is the wave travel. Sorry, this is the wave travels, and particles in the medium move like parallel. Yeah, and this I just like a it just like a push pull this like a string, and which makes like the particle in the medium move parallel to the direction in which the wave travels. So we call this kind of wave longitudinal like wave. Quickly moving the end of a spring back and forth send a wave in the form of a compressed region down the spring. Like the particles that make up the spring oscillate horizontally as the wave passes. This kind of wave we call it longitudinal wave. Okay, like actually, like the two most important types of earthquake quick waves are S wave and the P waves. The S wave is the transverse wave, and the P wave is a longitudinal wave. You can see here is the like a longitudinal wave, and the passage of a longitudinal P wave expands and compresses the ground it is expand and then compresses the ground. The motion is parallel to the direction of the travel of the wave. And the other one is S wave, transverse wave. And you can see like this wave just the wave like travels to this direction, but the particle just move up and down. Yeah, which make the ground move up and down, but the wave travels the direction like this. So actually the P waves, the longitudinal wave, like transfer faster, like travels faster. But the S waves are more distraction because you can see here, like the S wave, it will up, down, up, down, up, down. And then it will make the building like a cart. And then like maybe let the building fall down like that. But do you remember, we talk about if the earthquake happened and for a tall building, there will be a big, a terrible result if the P waves like a longitudinal wave in some condition. Do you remember that? Yeah. If there is a resonance and for the P waves, it's also very dangerous for us. Yeah, because you can see the P waves, it's up it's like a right, left, and actually for the building, because of the wind and something, it will oscillate. Is like a slightly. If this like earthquakes wave frequency is same with same with like a building oscillation, and it will like have the resonance situation, and then it will get a very big amplitude, and there will be a very terrible result. We talk about it, yeah. But usually, the S wave are more destructive. Only if the P waves has a frequency like same frequency with like the building like oscillate. Yeah, that would be like more terrible. Does it make sense to you? Okay, yeah, so the P waves are faster, but the S waves are more destructive. I think this is the same with the before one. And okay, this is like a model wave, and we have many kinds of waves, like a water wave, light wave, sound wave, and but they have some like specific rule, specific they share some same features, and there are some terms we need to familiar, like a mechanical wave, what is mechanical wave? The mechanical wave is just travel through some medium. And what is disturbance? Disturbance is a wave that passes through a medium. And also, what is like most waves fall into two general classes: transverse and the longitudinal like waves. Yeah, those are some basic terms. Okay, let's see what is traveling waves. Actually, we talk about the wave model. The wave model is built around the idea of traveling wave. Actually, a traveling wave is an organized disturbance that travels with a well-defined wave speed. We will talk about this more. And like when you drop a pebble in a pond, waves travel outward. How does a mechanical wave travel through a medium? To answer this, we must be carefully to distinguish motion of wave and the motion of the medium. Yeah, there are two different things. Yeah, uh, we will talk about more. If you drop a paddle in a pond, and there are some waves, so the waves travel outward, but like we need to be very careful for to distinguish like what is the motion of like a motion of the wave and the motion of the medium. Like a wave is not a particle, so we cannot use Newton's laws on the wave itself. Actually, the medium is made of. You can see wave it's kind of it's yeah, like I said, it's not a particle, it's not a thing, it's not like a real thing you can touch it. It's just a form, like a shape like that. Yeah, we cannot use Newton laws on the wave itself, but the medium is made of particle, so we can use Newton's laws to examine how the medium responds to a disturbance. Yeah, like if you put a drop a paddle in a pond, like what is the medium? Yeah, it is water. Like uh if you analyze the sound wave, what is the medium? It is air because this sound wave travels in the air. Does it make sense to you? So just pay attention, like the difference between wave and a medium. Yeah, we will talk about more in this section. Okay, let's see. First let's see the waves on a string. Yeah, this will help you to easily understand wave and the medium. Yeah, a transverse wave path traveling along a strength is shown below here. Like this is a transverse wave path. The curvature of the string due to the wave leads to a net force that pulls a small segment of the string up or down upward or downward. You can see the curvature of the string. Yeah, as a like a wave reaches this point, the curvature of the spring leads to a net force that pulls the string like upward upward. Sorry, let me try to. You can see if you like a up use this is a transverse wave, so which will be this this up down to give a wave to this string, and then if the wave travels here in the curvature of the string leads to a net force because here is a net force. This pulls the string upward. And after the peak has passed, the curvature of the string leads to a net force that pulls the string downward. Yeah, because you can see if you give move this string up and down, and there give an energy. This energy, for example, the this energy generate a force, and in this, for example, in this point, this force will make will push the string upward, and then the peak, after the peak pass, the curvature of the string leads to a net force like down, which pulls the string downward. Does it make sense to you? Yeah, this is how the waves travels on a string, and each point on the string moves perpendicular to the motion of a wave. Like here, sorry. Yeah, each point on the string moves perpendicular to the motion of a wave. Here, this is the wave direction, and this always like the like stream moves perpendilar to the direction of the motion of wave. So a wave on string is a transverse wave. That's the reason why we call it a transverse wave. An external force created the pulse, but once started, the pulse continues to move because of the internal dynamics of the medium. Yeah. This is why like this string will like move uh, up and down, like because once this there is a external force. For example, you use hand to give it a up down to move this string, it will create the pulse. But once this start, the pulse continues to move because of the internal dynamics of the medium. Yeah, this is this string like they said, oh, it can be can this wave can can travel. Yeah, does it make sense to you? Okay, let's check some like questions to let us to understand what we have already talked about. Like a wave on a string here is traveling to the right. At this instant, the motion of the piston of string marked with a dot is what? Yeah, if this wave travel direction is is this one. Yeah, is this one. And at this instant, the motion of the piston of string marked with this dot, it is up or down. Yeah, it is. Yeah, because you can see it travels like this. So this one, I think, yeah, it is easy to find. It will be up. Yeah, yeah, because you can see like this is a motion of motion of wave, and this is a motion of medium. Yeah, it should be pendulum. It should be like a up and then to the because yeah, it is the string will will goes to this direction. Does it make sense to you? Yeah. Okay. This is just the string wave. Let's talk about the sound waves. When a loudspeaker, like a cone, moves forward, it compresses the air in front of it. Yeah, I think this one. Yeah, when the loudspeaker receives an electronical pulse and pushes out sharply, this creates a compression of the air. Yeah, this compression is this disturbance. It travels at wave speed, like waves like a velocity sound. The speed is like sound speed. Yeah, and which means that, like when a loudspeaker like a call moves forward, it just compresses air in front of it, and this compression is a disturbance that travels through the air, like it's just like a wave. This sound wave is a longitudinal wave. Yeah, if you like, you can see the speaker. Uh, yeah, there is a if you know how the speaker what the speaker looks like, there will be uh, similar like a drum, and then it will move rather this direction, right, left, right, left, right, left. And then this generate a wave through travel through air, and this is the wave travel direction. Yeah, so you can see this direction and this direction is the same thing. So this sound wave is a longitudinal wave. Does that make sense to you? The motion of the sound wave is determined by the property of the air. Yeah, actually, yeah, because we talk about that. Once like you make this pose and the and how this wave travel in a string, it decided by the string. It's not decided by the like wave. Yeah, because by the medium. So the similar thing, yeah. If the sound wave is determined if after the speaker generates this like a wave, and the sound wave is determined by the property of air, by the medium. Yeah, that makes sense to you? Okay, like a wave speed, let's talk about wave speed. Actually, we talk about that. We just mentioned that after the wave generated, the wave speed actually is determined by the medium. Yeah, the wave speed does not depend on the size and shape of the pulse, how the pulse was generated or how far it has traveled. Only the medium that carries the wave. Yeah, so just sometimes maybe it's a little confused to understand, but think about the wave and the medium. It's like a different thing, and I give the energy to this medium, and this medium like move in a wave form. Does it make sense to you? Yeah. So this like for the strings, properties that determine speed are strings mass, length, and tension. The speed, like the wave speed, depends on the mass to length ratio, the linear density of string. Actually, yeah, here we talk about the string, sorry, the strings, like the property that determine speed are strings mass and length and tension. Actually, strings mass and length can decide the linear density. Yeah, the speed depends on the mass to length ratio. We call it the linear density of the string. Yeah, we use this equation to present linear density. The linear density characterizes the type of string we're using. For example, you use the plastic string or the iron string or some other material string. Yeah, and those strings linear density can be decided by the mass to length ratio. Yeah, and also the speed determined by the tension, and a string with a greater tension responds more rapidly, so the wave will move at a higher speed. Wave speed increases with the increasing tension, and a string with a greater linear density has more inertia, so it will respond less rapidly, so the wave will move at a lower speed. Wave speed decrease with increasing linear density. Yeah, which means the linear density is bigger and the wave speed will lower. Analyze a wave speed shows both of these trends. Yeah, velocity of string equal, this is tension. Sorry, this is the tension of the string, and this is linear density. Yeah, so which means if the tension increase, the velocity also increase. If the linear density increase, the velocity will decrease. Yeah, does it make sense to you? Yeah, like the wave speed on a stretched string with tension T and linear density like mu. Okay, let's continue. Let's check some questions to understand what we have learned. There are two waves. These two wave pulses travel along the same strength string, one after the other, which is true. Yeah, like this is the same strength string, which means the which means the and then which means this linear density is same. Yeah, because it's the same stretched string. I'm right. Yeah, and so which one? So which one is right? I think it's easier to get. It is equal. Yeah, because wave speed depends on the property of the medium, not on the amplitude of the wave. And even this amplitude is much bigger than this one. But because this is the same string, so the velocity is the same thing, is the same velocity. Yeah, because the velocity only depend on the tension and the like linear density. Yeah. Okay, that makes sense to you? Okay, let's see the other one. For a wave pulse on a string to travel twice as fast, the string tensor should be what? Let's write the v equal what? Square root 10. This is tension, and this is a linear linear identity. Am I right? So we the wave pulse on we want the wave pulse like travel twice as fast, which means we need two v. Now is v. We need two v. So the string tensor should be like a increased by what? It should be 4. Yeah, because if my the v new, if my string if my tension become 4 tension, and then like I will equal 2t mu, it is 2 the old v. Am I right? Does it make sense to you? So the answer should be A. Yeah, we just use this equation. Yeah, just try to remember this equation and what is mu? Like the like a identity linear identity. What is this? It is m divide L. Does it make sense to you? Yeah. Okay. Let's continue. Yeah, let's talk about this example problem. It's a biology problem. When does a spider sense his lunch? Yeah, all spiders are very sensitive to vibrations. An our spider will sit at the center of each large circular web and monitor radial threads for vibrations created when an exact length. Assume that these threads are made of silk with a linear density of multiple like 1 power negative 5 kg divide yeah, like the linear density is this one is these things under a tenth. Yeah, this is a linear tenth 0.5 and both like typical numbers. If an insect lands in the web 3 centimeters from the spider, how long it would take for the spider to find out? Yeah, it just let you to calculate the time. Am I right? Let me give you the strategy. When the insect hits the web, a wave pulse will be transmitted along the silk fiber. The speed of the wave depends on the property of silk. So what is speed of the web? Yeah, do you remember that? It is a square root. What is it? T divide what? Like mu is like linear density. Am I right? So here, from based on this number and this number, you can calculate the velocity for this wave, and the distance the spider and the insect, it's 30 centimeter, which means you have the distance, you have the velocity, and you can easily to get t. Am I right? T equal distance divide velocity. How long will it take you to get this distance with this velocity? Does it make sense to you? I think this is a typical traditional physics problems. Maybe you have already learned in high school. Yeah. So yeah, it's let's prepare. The spin of the wave on string is given by the equation 52. Yeah, this one. Sorry. Here, 50.2. Yeah, you can find it in textbook. And then we use this equation to calculate the velocity, and just put t here, mu here, and then we got the velocity is 200 per second. And the time for the wave to travel a distance d equal 30 centimeter to reach the spider is, yeah, the t should be d divided v. This is, and it will be 1.5 milliseconds. Yeah, it's very short, am I right? So, which means like when the insect drop on the web, and the spider will sense this like insect very quickly, like less in 1 second, just milliseconds. Does it make sense to you? Yeah, you can see if it is too long, if the time is too long, maybe the insect has already escaped. Am I right? Yeah, so spider webs are made of very light strings under significant tense, so the wave speed is quite high, and we expect a short travel time, important for the spider to quickly respond to pre-code in the web. Yeah, our answer makes sense. Otherwise, the insect will escape when the spider like find yeah, there is a food. That makes sense to you? Okay, let's continue. Okay, let's continue to talk about the wave speed. Just now we talk about the string, like string speed, string wave speed. Here, let's talk about the sound wave speed. Actually, sound speed is slightly less than the RMI speed of the molecules of the gas medium. Like through it does have the same like dependence on temperature and molecular mass. Yeah, like the sound speed in a gas at it, like it should read determined by like this equation. Sorry, should by this equation, and this equation here this is temperature. It will uh like m is the molar mass of the gas. Yeah, for example, for our air, like it should have the specific mass, and like for some if the sound like travels in some atmosphere just include just contains CO2, and it will have different it will have the different result, like if it travels in water, travels in uh, H H2 CO2, it will the M would be different, and this R is a constant that depends on the gas. Yeah, it should usually like if you know it is like a O2, and if it is H2, and this number is it will be fixed. It is constant that depends on the gas, and this Kb is Boltzmann's constant. Yeah, I think this one you should have already learned in high school or something else. Yeah, but Kb is Boltzmann's constant. Yeah, this one it's it will be should give you it's around um yeah, I will give it to you later. And the T is absolute temperature in Kelvin. Yeah. So if you know these things, and you can calculate the sound sound wave speed. Okay. Let's talk about the speed of a sound in air. And other gases increases with temperature. You can see as the temperature increase, the speed sound also will increase. Yeah. And here, for calculations in these chapters, you can use the speed of sound in air at 20 centimeter, 20 degrees, 20 degrees centimeter. Yeah, and 243 meter per second, unless otherwise specified. Yeah, like when the question let you calculate some speed of the sound, and you just use relate to the speed of sound, and you just use this number. Other, unless otherwise specified. At a given temperature, the speed of sound increases as the molecular mass of the gas decrease. Yeah, and you can see at the given temperature, the speed. Let me just write it down here, and V write it down. V equal R Tm. Yeah, like when the temperature is fixed. Yeah, and the mass, if the mass increase, which means the velocity will decrease. Yeah, does it make sense to you? Thus, the speed of sound in room temperature helium is faster than that in room temperature air. Yeah, because the helium, the mass for the helium is like smaller than the room temperature, the mass in room for the room temperature. The speed of sound doesn't depend on the pressure or the density of the gas. And you can see here, there is no like density of the gas. Yeah, the speed of sound that doesn't depend on the pressure or the density of the gas. The speed of sound in liquid is faster than in gases and faster in solids than in liquids. Yeah, because you can see usually the liquids the mass for the liquids is bigger than the gas in the gas for the gas and also the solids like mass for the solids is bigger than the liquids. That makes sense to you? Yeah, according to this equation. Okay. Yeah, this is some like a common spin of sound. Yeah, in some specific medium. Yeah, like in air, like if it is the temperature is 0 degree, sorry, 0 degree, and the speed will be 300, blah, blah, blah. And if it is room temperature is 20, and the speed will this, and it is in the helium, and this is alcohol. Yeah, it's just a liquid. Yeah, the speed is much bigger. And water, human, tissue, yeah, ultrasound, I think. And the lead, this is the solids material. Yeah, and you can see, and in the diamonds, it is yeah, very, very high because yeah, maybe because mass is big, very big, like big in one unit like that. Okay, let's talk about these questions. A wave bounces back and forth on a guitar string. This is responsible for making the sound of the guitar. As the temperature of the string rises, the tension decreases. This what increase the all does not change or decreases the spin of the wave on the string. Yeah, like I said, we just write the spin. This one is a little tricky. Yeah, here you can see there is a wave. Here is a wave. It didn't tell you this is a sound wave. Am I right? So which means it just like a regular wave, and the medium is what is a guitar string. So this is a string. So then we need to use this T, this is tension, and mu, this is like linear density. And so we need to use this equation. And for now, like this for this equation, it's just the speed just depend on the string tension and the linear density. So when the tension decreases, yeah, what is the like a speed change? It will also decreases. Am I right? So just like don't be confused. Yeah, this wave is just now a sound wave. It's just like a vibration, like a uh like a in the spring. Yeah, does it make sense to you? Okay. Yes, yeah, it decreases. Okay, let's talk about the other like examples. The spin of sound on Marses, like on a typical Martin morning, the very thin atmosphere, which is almost entirely carbon dioxide. Okay, let me try to check how to. Dioxide. Okay. Okay, let's check about this example, like the spin of sound on Mars. Like on a typical Martian morning, the very thin atmosphere, which is almost entirely carbon dioxide, is frosty, like negative 100 degrees. What is the spin of sound on such a morning? And what approximate temperature would the speed be double this value? Okay, yeah. Here we notice the question asks the speed of a sound, which means we need to use these equations. And this equation, like you can find it in textbook equation 50.3, and we just talk about this one. And give the spin of sound in terms of the molar mass and the absolute temperature. We will assume that the atmosphere is composed of pure like CO2. Yeah, we just do a assumption. Yeah, and then we can use this equation. Okay. The molar mass of CO2 is the sum of the molar masses of the constituents, like this one for yeah, this one for C and this one is for O. And because CO2 is 1C and 2O, so and the mass is equal 12 plus 16 plus 16, it will 44 gram per mole. So this is 0.044 like a kilogram. Yeah, does it make sense to you? I think this you have already learned in like high school or in like college physics one. Yeah, and the absolute temperature is this one in like for the CO2, and the carbon dioxide is a triatomic gas. So this one you can easily get. It's a fixed thing. Yeah. So here the speed, you can use this equation to get it. Actually, this one is a specific, is a fixed value for CO2, and then this one is also like you can got it, and this one, yeah, we can got it here, and this one we also can got it. So it is 210 meter per second. This is the speed sound in the on Mars. Does it make sense to you? Yeah, like this. Actually, this question is easy, but the problem is, how can you get this kind of like a value? Like because this is CO2, CO2. So there are some like specific value here. This one, and this one, this one, and the temperature. Also, you can check it. Like usually what's the temperature in like on Mars, and then you can use this value to calculate the velocity. Does it make sense to you? Yeah. So don't like afraid of this one. Yeah, you can. Okay, let's continue talk about the wave speed. Yeah, and you can see we talk about the wave speed on stream and also the sound wave speed, and also like let's talk about the electromagnetic waves such as light travel at much higher speeds than mechanical waves. Actually, the speed of light, c, is the speed that all electromagnetic waves travel in a vacuum. The value of the speed of light is a constant. Yeah, if you already learned something about the physics thing, and we know the speed of light is a constant. It's around this three, yeah, this value. Although light travels more slowly in air than in a vacuum, this value is still a good approximation for the speed of electromagnetic waves through air. At this speed, light could circle the like Earth 5.75 times in seconds. Yeah, so the light speed is very quick. Yeah, light wave speed is very quick. Okay, let's see an example. How far away was the lightning? I think actually this is a very typical like a physics problem. During a thunderstorm, you see a flash from a lightning strike. 8 seconds later, you hear the crack of the thunder. How far away did the lightning strike? Yeah, it just let you to calculate the distance. Actually, when you see the light, because the light, like we talk about the light the light wave travels very fast because the speed of light is just around this value. Okay, so this value, which means when you see the lightning, which means it's just the time like it happens. The 8 seconds later, you hear the cracking of the thunder, which means this like sound wave have already travels 8 seconds. Am I right? And we know like the sound sorry, the sound like the sound what is the sound wave speed? Yeah, we have already talked about that in there. Yeah, in like air it is around like 343. So you can use that value to calculate this, which means here like the sound has this velocity 3 kilometer maybe seconds 3 for 3, and then it has already traveled like 8 seconds, which means multiple 8, and then you can get the distance, how far away the light traveling. Yeah, I think here is the strategy, like two different kinds of waves are involved with very different wave speed. The flashing of the lightning generates light waves. These waves travel from the point of strike to your position almost instance, instantaneously. Yeah, because it's at the same time you can see the lightning, and the strike also generates the sound waves that you hear as thunder. These waves travel much more slowly. Yeah, so you can see here we have the time for lightning to travel 1 mile is around like this things. Yeah, you can see like yeah, 1 mile is just like 1,000 blah, 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 blah meter, and then it will divide the letter, which means like this short time and this like light will travel 1 mile. Yeah. Okay. So yeah, like we talk about that, we are given the time to an accurate only blah blah blah. So it's clear that we can ignore the travel time for the light flash. The delay between the flash and the thunder is simply the time it takes for the sound wave to travel. When assume that the speed of sound has its room temperature, 20-degree value of 343 meter per second. During the time between seeing the flash and hearing sound, the sound travels a distance. Yeah, this is just what we talk about. Yeah, it will be 2.7 kilometer. Yeah, does it make sense to you? Yeah. Okay. Let's do an assess. This seems reasonable. As you know from causal observations of lightning storms, an 8 second delay between the flashing of the lightning and the cracking of the thunder means a strike that is close but not too close. A few kilometers seems reasonable. I'm right. If it is too far, you cannot see it. Yeah. Okay, let's continue to, yeah, you can try it yourself, like a distance to a lightning strike. Sound travels approximately 1 kilometer in 3 seconds or 1 mile in 5 seconds. When you see a lightning flash, start counting seconds, and when you hear the thunder, stop counting. Like divide the result by 3, and you will have the approximately distance to the lightning strike in kilometers. Divide by 5, and you have the approximately distance in miles. Yeah, does it make sense to you? You can try. Yeah, because this is summer, I think maybe you will find the opportunity in the several days. Yeah, any question, just let me know. Yeah, this is not difficult to understand. You can see when you, let me explain again. When you see the, actually when the lightning and the thunder happens at the same time, but you will always see the lightning firstly because the light wave travels very fast, and uh, we assume there is no like time difference. When you see it, you can see the lightning at the same time when it happens, and after that, and you can hear the thunder because the sound wave travels much slower than the, and then this like time difference is how long the sound wave travels, and we know the velocity for the sound wave. So then we can calculate the distance, use the velocity multiple the time. Does it make sense to you? Okay, let's see the other very important thing. Yeah, section 50.3, graphical and mathematical description of waves. Yeah, firstly, let's talk about a graphical description of waves, and then the mathematical description of waves. Before we talk about the graphical description of waves, let's talk about what is a snapshot and a historic graphics. A snapshot graphic shows a wave's displacement as a function of position at a single instant of time. Yeah, you can see the snapshot. This is a see. Yeah, this is a snapshot graphic. And this graphic shows a wave's displacement. This is a wave's displacement as a function of position, yeah, at a single instance of time, in one specific time, like a, what's a wave's displacement, and what is it looks like that. Does it make sense to you? Okay, and as the wave moves, we can plot a sequence of snapshot graphics successive frames from a video. Yeah, like you can see as the wave moves, and you can see this is a wave, and this is the distance like that. This is a displacement, and at time one, and the wave moves here. It's just like that, and at time t2, and this wave moves here, and the t3 this move moves here. Yeah, the wave always moves without changing shape because we assume there is no other assumption. Yeah, there is no friction. Yeah, it's ideally like a wave movement. Yeah, the wave moves forward delta x to v delta t during time interval delta t. Yeah, does it make sense to you? Okay, these graphics show the motion of the wave, but that's only half the story. There is another half of story. Yeah, now we want to consider the motion of the medium. Yeah, you can see in each of the graphics we have placed a lot located at position x1 at one point on the string. Yeah, you can see here. Yeah, in this position, yeah, there is for example, sorry, yeah, for example, here there is a position, yeah, in this for example, there is a wave path, and in this there is a position x1 at one point on the string. We use the vertical position to show the motion of the one point on a string. This is called a history graphic. Yeah, yeah, we call this one just one snapshot. One the other one this is one a snapshot. This is another one, two snapshot, three one snapshot, and then if we yeah, this is a yeah, I think this is a T1 snapshot. This is T2 snapshot. This is T3 snapshot. This is T4 snapshot. You can see as the time pass, yeah, and this wave will move forward to this direction. Yeah, does it make sense to you? Yeah. Okay. And if we graphing the motion of one point in the medium gives a historical graphic, which means this point, yeah, just this point. Let me change the other color. Sorry. Oh, yeah, this point. Yeah, this point. Yeah, this point is just this point. Yeah, because the wave moves, travel. So this point will show in this wave here and here in time three. This is in time one, time two, time three, and time four. And if we draw a history graphic, which means you can see a historical history graphic, which means it related to time. You can see the axis is time, and in the team one, the point is here. In the team two, the point is here. And in the team three, the point is here. And the team four, the point is here. Yeah, and then we just connect it together, and it will give you the history graphic. Does it make sense to you? Yeah, yeah, because you can see, for example, let me try to draw it by myself. Here is the T time, and here is displacement. And in team one, all right, it the T1 and it is in this the displacement is here is equal this one. In T2 and the displacement equal this one. And T3, yeah, it is equal this one. And in T4, it is this one. And then you just connect them together. Yeah, it's the same thing here. Does it make sense to you? This is when you draw how can you draw a history graphic? Yeah, does it make sense to you? Okay. The snapshot graphs are pictures of the waves at a particular instance in time, like a specific time, in a specific time, like a T1, what is the wave is, what does the wave look like? T2, what does it look like? T3 look like T4. And you can see the if you want to observe a long uh, because the waves usually will keep a long time. So if you draw it from T1 to maybe 100 T1, it will be very long. But in the history, it will you can see as a T pass and what's a specific point look like. The historic graph is a record of the motion of one point in the medium over time. Does it make sense to you? Yeah. Okay. Let's see some quick chat questions. Okay, yeah. This is a snap graphic at 1 second of a wave pulse traveling to the right at 1 meter per second. Which graphic below shows the wave pulse at -1 seconds? Yeah, does it make sense to you? Yeah, which means this wave like this wave travels in this direction, and let me try to put it back to yeah, yeah, in this direction. This is when the t equal 1 second, which means the speed is 1 meter per second, and which means in 0 seconds, and it will back 1 meter. Doesn't make sense to you? It's just like this. This is in the 1 second. If it is -1, which means it will back another 1 unit, 1 meter. It's just like this. Am I right? Yeah, so it's obvious. And the answer should be A. Does it make sense to you? Yeah. Okay. Okay, let's quick check this problem. The graphic below shows a snapshot graphic of a wave on a string that is moving to the right. Let me, sorry. You don't see the answer, am I right? Okay. Yeah, and it moves to the right. A point on the string is noted. Here is that point. Which of the choice is the correct histograph for the subsequent motion of the point? Yeah, you can see as a wave travel, and this for this point it should just and 0 and a smaller one, and then this one, and then it should be like the verse, this version, am I right? So which means which one? It's obvious. It's B. Am I right? Does it make sense to you? Yeah, because you can see as the time as the wave pass, yeah, as the time pass, this wave will move in this direction, and this is the same point. This wave and it should be like a uh, in this point, in this point, in this point, we, as a t, this is T1, T2, T3. This is T1, T2, T3. It's like this. Does it make sense to you? Yeah. Okay. And let's check. Okay, now we have already learned using the snapshot graphic to describe the wave, and also use the history graphic to describe the wave. Now let's about the mathematical description of sinusoidal waves. Yeah, and you can see if we observe the waves we will see like many waves just moves like a sinusoidal wave. Yeah, so let's try to explore like the mathematical description of sinusoidal waves. Actually, a sinusoidal wave is a type of wave produced by a source that oscillates with simple harmonic motion. Yeah, you can see. Yeah, since it this wave was this wave produced by a source that oscillates with simple harmonic motion. So this wave we call it a sinusoidal wave. The amplitude A is the maximum value of displacement. The crest crest has have displacement of A, and the throws has a displacement of negative A, which means yeah, when you see that waves, for example the water wave, and you can see there is a top thing, it's crest, and we call it it has a displacement N, and then there will be a throws, and it will be the negative A. Yeah, that makes sense to you? And it's just like this. Yeah. Okay. And the wave, like SHM, simple harmonic motion, is repetitive, and the wavelength lambda is the distance. Yeah, this the wavelength here from here to here. Yeah, this we call the wavelength is the distance spanned in one circle of the motion. Yeah. Because there is it's not t, so we cannot call it a period. It's just like a the distance this wave like runs, and so the wavelength lambda is the distance spanned on the one circle of motion. At time t, that at time specific t, for example here is time t, the displacement as a function of distance is just like this. Yeah, because you can see it is a simple harmonic motion, so we can use a similar equation to represent it. Like this is y is the displacement, and this a is the maximum, like a cosine, because this is a cosine function. Does it make sense to you? Yeah. Okay. A historic graphing of the motion of one point of the medium as a function of time is also sinusoidal. Yeah, the graphic looks the same, but the meaning is different. You can see here, uh, which means actually these two images is not like a historical historic graphic, because historic graphic it must like the axis it must be t in time. Yeah, like each point in the medium oscillates with simple harmonic motion as the wave passes. Yeah, like the history graphic for sinusoidal waves, and the history graphing of the motion of one point of the medium as a function of time is also sinusoidal. And like that, the graphic looks the same, but the meaning is different. Each point in the medium oscillates with simple harmonic as the wave passes. Yeah, I think that obvious. The like this, yeah, this is like a historic graphic. The period t. of the wave is the time interval to complete one circle of motion. The wave frequency is related to the period t. Yeah, this is the same thing. Yeah, exactly the same as in like a simple harmonic motion. Therefore, the motion of the point is this one. Yeah, this is the motion of the point. Yeah, what's the difference between this one and you can see here the variable is t. Am I right? And period. And but for this is historiography, and this is like a snapshot like graphic. Yeah, and this is the variable is x, the like the distance. Yeah, and this is also, and this is a one wavelength. Yeah, does it make sense to you? Yeah, it's different, but it has a similar form. And when combine the mathematical expressions for the disciplines as a function of position at one time and the disciplines as a function of time at the one position, like we combine those two functions. Yeah, which means we have a function. We have a function. This function like related to x and t, and which means like here there is a yx equal what? A cosine 2 pi x divided omega, and divide lambda, like yt equal A cosine 2 pi t divided t. Am I right? And we, okay, let's check those two equations. And those two equations. And you can see this is two equations we have already talked about. And we want to combine them together. Actually, we can write this equation like this, y x0, which means when the the time is has not passed. Yeah, it is like x omega. Yeah, and then we just write like 0t equal, yeah, because it is we want to, this is right move, so we just use cosine like negative 2 pi t over t, which means at time t, and when the like displacement is 0, and then you can see we can put them together just like this. Yeah, this is why this equation come out. Yeah, does it make sense to you? Yeah, when it is 0, it's just like this equation. When this is 0, it's just like this equation. If we combine them together, and then we just like get this equation. Okay, and for this like the notation yxt indicates that the displacement of y is a function of two variables x and t. Yeah, here I have already written it down. And yeah, those like this displacement and depend on the two variables s and t. In the figure, we have graphed the equation at 5 instants in time. Like this is t0, like a quarter period and half period, 3/4 period and period. As the time t increases, so does the position x of this point. If the like time you can see passed, and the position t, position x, you can see here is x, also moves to the right. Does it make sense to you? One full period has elapsed. Here you can see here is one full period elapsed, and the wave has moved one full wavelength, which means as the time passed one period, and the wave will like pass one full wavelength. Yeah, does it make sense to you? Okay. And this is for wave traveling to the left. Actually, it's similar to the right, but you can see it's a different direction. So we just replace here is -2 plus. Does it make sense to you? Like know that a wave moving to the right, like the plus x direction, has a negative in the expression. While wave moving to the left, it is like a minus x direction has a like a plus in the expression. Actually, it doesn't make sense. For example, you see like if you move some like for example, here is a YKT. It's just like this line. That makes sense to you. And if you like YK like x minus 1, which means it will like move to right. Does it make sense to you? Yeah, it's a similar thing. Yeah. Okay, let's continue. Let's talk about this question. The period of this wave is, yeah, you can see here. We just talk about like one full period has elapsed and the move has moved move one full wavelength. Here the one full wavelength is two like a meter, which means this is on just one period. So we just need to calculate the t for this wavelength. It is 2 meter, and we just 2 divide 1. It is 2 seconds. Does it make sense to you? Yeah. This is 2 seconds. A sinusoidal wave moves forward one wavelength in one period. Yeah, we just need to calculate how long it will move 2 meter. Does it make sense to you? It is 2 seconds because 1 second is 1 meter. Okay, let's keep doing. For this sinusoidal wave, what is the amplitude? Yeah. Okay. The amplitude is what? Do you know that? I think this one is very obvious. Yeah, you don't even to calculate anything. Amplitude means the maximum displacement. Am I right? So it's just this here. I'm sorry. It not related to the velocity times and wavelengths. Am I right? So it's just like a one. Any questions? Okay. For this sinusoidal wave, what is a wavelength? I think this also, yeah, very easy to tell. The wavelength is just one one period for one repeat form. Am I right? So it is what? 2 meter. Yeah, this is easy. Okay, let's check an example. Determine the rise and fall of a moving boat. A boat is moving to right. You can see here. Oh, sorry. Here is a boat, and this boat is moving to right at 5 meter per second with respect to the water. Yeah, and an ocean wave is moving to the left. Yeah, here is a motion wave to the left. Opposite is the motion of the boat. The waves have 2 meter between the top of the crest and the bottom of the swirls. The period of the waves is 8.3 seconds, and their wavelength is 110 meter. At one instant, the boat sits on a crest of the wave. 20 seconds later, what is the vertical displacement of the boat? Yeah, actually, I think this one is not that difficult. We just need to use the equation we have already learned. Yeah, because here we know from the everything this one give to us, and you can see because the wave is moving to the left, the wave head as a function of the position and the time is given by equation 50.8 from the you can check it in the textbook. Yeah, and from the boat speed, we will find its position x at time t equal 20 seconds, and then use equation this one to find its height. We begin with a variable overview, like as in the figure above, let t equals 0 be the instant the boat. Here is a t equals 0, and is on the crest. Yeah, here is the crest, and draw a snapshot graphing of traveling wave at that time. Okay, we can try to. The boat begins the distance between the high and the low points of the wave is 2 meter, which means what? The wavelength is 2 meter. Am I right? And the amplitude is half this. So the distance between so the A equal 1. The distance between high and low points of the wave. Oh, sorry, my mistake. Like the distance between the low and high and low points of wave. This wave, the whole low and is 2 meter. So amplitude is half of this. So the A, like the maximum displacement, is 1. The wavelength and the period are given in the like a problem. The wavelength, we know it is 110, and the period is like 3.8.3 seconds, and the distance is 1 meter, and here is t equal like 0, and for now we want to get the when the like its position x at t equal 20 seconds, and the boat, the velocity boat, yeah, is like here. It's moving to right at the velocity boat is is 5, and yeah, and the x equal 0, and the y equal like a equal, here is the y here, like at this time, and the x equal 0 because we just like graph is t equal 0, and the y here is equal a. Does it make sense to you? Okay, like the boat is moving to the right at 5 meters per second at t equal 20 seconds. The boat is at the position, this one, like a velocity multiple the seconds, it is 100 meter. Yeah, we need to find the wave's displacement at this position and time. Substitute known value for amplitude, wavelength, and the period into equation. Yeah, this is the equation 58. We have already talked about this. Yt equal like a cosine 2 pi, like x divided by omega plus, because it moves to like left. The wave moves to left, so it is plus. And then yeah, so we just like put everything in this equation, and at t equal like 20 seconds at xf equal 100, the both displays on this wave. You can see here is here we can know the t, the x equal, and the t is, we just replace the x t here and 2 pi, we know that, and yeah, then we know the both displacement equal this one. Yeah, don't forget that the calculator you must be in reading mode when you make your final computation. Yeah, you can see the final displacement is negative. Don't see yeah, which means that the boat is in a storm of a wave, not underwater. If you see there is a negative symbol, and don't be afraid, don't be feel weird. Is this boat is not underwater? It's just in a like a thrones. Yeah, you can see the wave. Yeah. I think someone like go to the lake, go to the sea, and the wave. Actually, some waves are very big. Am I right? You can see when you negative, which means you are in the thrones. Throne. Yeah, that makes sense to you. Okay, let's continue. Okay, check. Let's review the fundamental relationship for sinusoidal waves. Actually, during a time interval of exactly one period t, each crest of a sinusoidal wave travels forward a distance exactly one wavelength lambda. Yeah, actually, we have already talked about this just now. Yeah, which means like we know the velocity equal distance divided t, and so the which means like the velocity for this like wave, we can calculate using this equation is lambda divided, because for a period and the wave the wave like move wavelength. Does it make sense to you? Yeah, in terms of frequency, the velocity of the wave, like you can see, you can because one f equal 1 over t. Am I right? Does it make sense to you? Yeah, so the relationship between velocity, wavelength, and frequency of sinusoidal wave is just like that. The velocity equals the wavelength divided t. Also, like all the v equal the wavelength and multiple frequency. Yeah, if you know the wavelength and the frequency of the period, you can know the velocity. Yeah, okay. Let's check about these questions. And for this sinusoidal wave, what is the frequency? You can see here the wavelength we can tell from this graphic. So it is 2m, am I right? The velocity is 200 meter per like seconds. We know the v equal what? The lambda multiple f. Yeah, we just talk about that. And here the velocity is 200, lambda is 2, so f equal what? It's obvious, am I right? 100. Okay. Yeah, it's 100. Okay. Let's try to like summarize what we learned in this class. Yeah. Yeah, many things, am I right? So, but don't worry, we can like summarize something for you. Yeah. Wave speed is determined by the medium. Just remember, the wave speed is only determined by the medium, not like the other thing, not like the initial force or something else. Yeah, for wave on a stretched spring. Sorry, for wave on a stretched spring, and you can see the like velocity uh for the wave, you can determine it by the string tension and the string mass divided by length. We call it like a linear density. Yeah, do you remember that? Okay. And for sound wave in a gas, yeah, we just use this equation, and this velocity sound wave is actually here. This lambda, this is a constant value. It usually we will give in the question. It will give to this value. Also, this one is also like constant value, and this is the temperature. Like for now, like in a room temperature, in some like yeah, weird temperature, and this is a like a molecular mass. For example, if you are in like in like some planet Mars, and there is only CO2, and you can use like a molecular mass to calculate this mass. Yeah. We have already talked about one example. You can review that. And for example, at room temperature in the air, and the sound wave velocity is just like this. And in a vacuum or air, the speed of that is this. Yeah. And like a sinusoidal wave moves one wavelength in one period, given the fundamental relationship. This one actually, yeah, we talk about a lot in this part, but the most important thing is just this equation. Yeah, usually like if you can calculate the frequency or the period, you know the wavelength, and you can know the wave of the speed of the wave. And as a sinusoidal wave travels, each point in the medium moves with simple harmonic motion. Yeah, you can see as a like a sinusoidal wave travels, each point in the medium. Yeah, it just moves with simple harmonic motion. Yeah, we can like represent it in like a sinusoidal function. Yeah, you can find this in like a textbook page 528. Okay, this is what we today we talk about, and yeah, and hope hope you can learn something about the wave. Yeah, just like remember today we focus on the wave on the spring and the wave in a sound wave, and also a little bit like light wave, but only uh, like the spin of light wave. Yeah. And also we talk about a sinusoidal wave, like moves one, like the relationship between the wavelength and the period and the like the velocity. And yeah, uh, Okay, this is the class for today. And if you have any question, just let me know. Okay, thank you. Bye. Mm.